So today I will be introducing to you SOMIX, a low-power autodyning receiver architecture that achieves a long range. So this is joint work with Rajashekar Reddy, who is also here, and Wenqing, Prabal, Dutta, and Ambuj Varshney from National University of Singapore, Uppsala University, and UC Berkeley. When considering the architecture of wireless embedded systems, we see that the core components include sensor, for example, like an accelerometer, and a processor, like the microcontroller, and radio transmitter for broadcasting information, like as RF signals. Over the past few decades, we see that sensors have become much more energy efficient, now consuming just tens to hundreds of microwatts. Also, processing technology have significantly improved in terms of both area and power, and they consume hundreds of microwatts. However, we see that improvements in radio communication efficiency have not kept pace, mainly due to their reliance on analog components, and they consume tens of milliwatts. So we see that there has been significant amount of work improving transmission, especially focused on applications like wireless sensor networks that prioritizes transmission. Over the past decade, backscatter mechanism has been extensively explored to reduce power consumption in transmission, and they have achieved transmission at few tens of microwatts. However, even in backscatter tags that operate in very tiny power budgets, we see that there's little to no improvement in the tag side receiver. They mostly use the same vanilla envelope detector used in UHF RFID tags for reception. They have limited sensitivity and does not support phase or frequency information and are unable to support complex modulations as well. So we see that this has resulted in asymmetry in low power transmission and reception. Low power transmitters support complex modulations and several meters of range, but such low power receivers does not exist. And with emerging applications and traffic patterns which are reception dominated, for example, like AR/VR glasses and earables, we see that reception needs to be given the attention that it requires. So moving to receiver architectures, we identify three main receiver architectures. First, the heterodyne or frequency conversion architecture. So in these architectures, the high frequency signal is converted to an intermediate frequency signal that can be easily processed and demodulated. And for this, they rely on power-hungry components such as the local oscillator and mixer. And the second type of architecture is the vanilla envelope detector architecture. While they are low power, they have limitations due to their reliance on Schottky diodes. They have low sensitivity and they are unable to support complex modulations and modulation schemes. So there's one other interesting architecture that we identify from literature. That is the external local oscillator architecture. Here, in these architectures, the generation of the local oscillator is offloaded to the transmitter or to an external device. For example, mixing. They support complex modulations at very low power. However, they rely on a support tone from the transmitter itself. So these architectures rely on an external carrier or helper tone. Here, we see that there's a need for low power receivers that overcomes or minimizes these constraints. So we present SOMIX. SOMIX can reliably receive signals transmitted from over 100 meters. It is an autodyning receiver which locally generates the carrier and self-mixes with the incoming signal to obtain a down-converted signal. SOMIX front-end does this while consuming less than 100 microwatts of power and achieving a sensitivity of minus 70 dBm. This is roughly 20 dB higher sensitivity compared to Schottky diode-based receivers. To improve the stability of the local oscillator, SOMIX optionally relies on an injection locking signal that can be from a source of over 100 meters away. So how do we do this? Let's compare the architecture of SOMICS with conventional heterodyne receiver. In a conventional heterodyne architecture, the local oscillator and the mixer are the most power-consuming components. So in SOMICS, we replace these power-consuming components with a single circuit, the tunnel diode oscillator, which is low power and performs the function of both the local oscillator and mixer. Tunnel diode, or Esaki diode, is a Nobel Prize-winning invention. Tunnel diodes exhibit negative differential resistance. Negative differential resistance is a phenomenon where an increase in voltage leads to a decrease in current over a certain range of operation. So if you look at the IV curve of the tunnel diode 1N3712, you would see that in the y-axis you have the current, and in the x-axis the voltage. And in the region of interest, as the voltage increases, the current decreases. So, and most importantly, this happens at very low voltages and current consumption. So this property of tunnel diodes allow them to be used in oscillators and to maintain sustained oscillations. Therefore, we build an oscillator using tunnel diodes. So here, we have the tunnel diode, and to bias it in negative region, we use a biasing network. And we use a resonance circuit to build an oscillator oscillating at 868 megahertz. When this circuit is received with a modulated RF signals, the nonlinearity of the tunnel diode oscillator self-mixes the incoming signal with its own locally generated signal. So here, the locally generated signal from the tunnel diode oscillator is mixed with the received signal all in a single circuit. And this is called self-mixing or autodyning. This completely eliminates the need for a separate mixer stage entirely. As a result of mixing, we observe down conversion. Down converted signal is observed at the frequency difference between the reception signal and the local oscillator frequency. So here, the plot shows the RF frequency band and the IF frequency band. So in the IF frequency band, you can see the reception signal and the down converted signal in the IF frequency band. As a result of down conversion, we see that there is conversion loss. Conversion loss is the power difference between the incident RF signal and the down converted IF signal. So we see that SOMICS front end has a fairly consistent conversion loss of about 25 to 30 dB, even when changing the transmitted signal strength or the intermediate frequency. We take this into consideration when we build the following stages of the receiver. In order to complete the receiver end-to-end pipeline, as well as demonstrate SOMICS front-end capabilities, we develop a simple 2FSK receiver. Here, we obtain the down-converted signal from the SOMICS front-end, and then we pass it through a pipeline that contains a passive bandpass filter, a two-stage amplifier providing up to 58 dB gain, and a 1-bit ADC over thresholding circuit. The filter is designed such that the passband converts the 2FSK signal to an ASK-like signal that can be interpreted using a single comparator. Going back to the tunnel diode oscillator, using the tunnel diode oscillator for generating local carrier signal poses a challenge. Tunnel diode oscillators have low frequency stability. That is, the frequency drifts with time, nearby motion, and even environmental factors such as temperature and humidity. So what you see here is drift of frequency due to nearby motion in SOMICS RF spectrum and IF band. So we rely on a phenomenon called injection locking. Injection locking is where an oscillator locks its frequency to that of an external signal. And for this to happen, the external frequency should be close enough to the natural frequency of the oscillator. We use an external emitter device and provide an external signal and observe that this stabilizes the local oscillator signal. Looking in detail, we see that SOMIC's receiver can be injection locked with an external signal from a source kept over 100 meters away. And we also observe that varying the injection locking signal does not affect the SNR of the down-converted signal, even when the injection locking signal is as weak as minus 70 dBm. This gives a lot of flexibility for deployment of the emitter as well as the SOMIC's receiver. We also observe that an unsuppressed carrier transmitted with reception signal allows SOMICs to completely avoid the emitter and achieve similar range. An unsuppressed carrier is one which the carrier wave is transmitted along with the modulated information signal. So here, FC is the carrier, and the sidebands carry the modulated signal. One classic example of this is AM radio broadcasting. Moving into the evaluations, we conduct multiple evaluations to assess the front-end performance. Considering the power consumption, the SOMIC's front-end consumes 100 microwatts. The demodulation pipeline containing the IF amplification and digitization consumes 150 microwatts. So in total, it consumes 250 microwatts. This is over 110 days on a single coin cell. We also assess the sensitivity of the SOMIC's front end. For this, we use an wired experiment setup to assess the sensitivity, and we provide weak signals ranging from minus 20 to minus 80 dBm. We observe that SOMICs achieves a sensitivity of minus 70 dBm, considering a minimum SNR of 10 dB. This is roughly a 20 dB improvement in sensitivity over conventional Schottky diode-based receivers. We also evaluate SOMIC's range in complex indoor non-line-of-sight environments with walls, multipath, and across floors. For this experiment and the following experiments, we use transmitter transmitting at 30 dBm power, which is the maximum allowed by FCC regulations. We place the emitter 24 meters away from SOMICs at an non-line-of-sight location separated by multiple walls and obstructions. So here, we see that SOMICs maintains communication up to 54 meters, even in a complex indoor environment. This suggests that SOMICs can reliably receive signals in practical deployments where walls and obstructions are common. We also evaluate SOMIC's range in line-of-sight outdoor range, and for this, we use an outdoor experimental setup and place the carrier emitter 25 meters away from SOMICs and vary the transmitter's position. So here, we observe that SOMICs achieves over 100 meters in range in line-of-sight environment. And also, at this location, the signal is still around 40 dB, suggesting that much longer ranges are feasible. We repeat the same experiment by transmitting an unsuppressed carrier and removing the emitter device. And we see that we can still achieve similar range when using an unsuppressed carrier in the absence of an external emitter. We also evaluate the SOMIC's end-to-end pipeline. So by using the end-to-end pipeline, we conduct experiments to evaluate the bit rate, and we see that the demodulator can support bit rates up to 10 kilobits per second. This is limited by the design choices of the demodulation pipeline, such as IF frequency, low power amplification, and 1-bit ADC. We also conduct much more evaluations, which are detailed in our paper. So, in conclusion, SOMIC's front end. SOMICs is a low power autodyning receiver that leverages a tunnel diode oscillator to perform self-mixing. It achieves this while consuming less than 100 microwatts of power, and SOMICs achieves a sensitivity of over minus 70 dBm, which is 20 dBm improvement over Schottky diode-based receivers. Also, SOMIC supports long-range receptions, achieving over 100 meters in outdoor line-of-sight environments and up to 54 meters in complex indoor scenarios. SOMIC's front end presents a novel architecture that opens up new possibilities for developing low-power receivers. Thank you.
Any questions for the speaker?
Thank you for the talk. Do you folks have any live demos of operation of your network?
I'm sorry, I didn't.
Do you have any live demos available of how your network operates? Like videos or data sets supporting how the system is working?
I think we have recordings of the data that we made, but also we have the live prototype back at the university. So SOMIC is a very small circuit with the tunnel diode oscillator. So we have the back end separately and the front end, which could which requires very little setup to work. But yeah, we could demonstrate if required.
So how difficult it is for you for others to replicate your setup, just to play it?
Replication is a bit challenging in terms of tunnel diodes because of the availability of tunnel diodes, because tunnel diodes are currently not being manufactured. But other than that, the architecture seems quite straightforward.
Okay, thank you.
Thank you for the question. Thank you.
Okay, let's thank our speaker one more time.